One of the most classic games in the field of game theory is known as the Battle of the Sexes. And here's the setup for this game. Imagine that a man and a woman are in a relationship, and on a night out, they can either decide to go to the ballet or they can go to a boxing match. Now, the woman prefers to go to the ballet, but the man prefers the boxing match. But here's the important part. Both of them prefer to be together doing the same activity rather than being separate doing different activities. So here's how we can represent this situation using a payoff matrix. So we have a woman who can choose to decide to go to the ballet or the boxing match, and we have the man who can also go to the ballet or the boxing match. Now, if the woman chooses ballet and the man also chooses ballet, then the woman gets a payoff of 2, while the man gets a payoff of 1. So in this case, the woman gets the higher payoff, because remember, she's the one who prefers to go to the ballet. But instead consider the scenario where the woman chose a boxing match and the man also chose a boxing match. Well, in that case, the woman gets a payoff of 1 and the man gets a payoff of 2. So in this case, the man gets the higher payoff because remember, he prefers the boxing match. And then also notice that if they choose different activities, so if the woman chose boxing and the man chose ballet, they would both get a payoff of 0. Or if the woman chose ballet and the man chose boxing, again, they both get a payoff of 0 because they went to different activities. And remember, they both prefer to be together doing the same activity rather than being separate. So let's see how we can find the Nash equilibrium in this particular game. So we'll start by imagining that we're the woman. Put yourself in the woman's shoes. She will say, okay, if I'm the man, if the man chooses ballet, which should I choose? Should I choose ballet or should I choose boxing? Well, if I choose ballet, I have a payoff of 2. If I choose boxing, I have a payoff of 0. So obviously 2 is the better payoff. So I should choose ballet. So let's underline that too. And then the woman will say, okay, but what if the man chooses boxing? Should I choose ballet or should I choose boxing? Well, boxing offers the higher payoff of 1, so I should choose boxing. So let's underline that one red as well. Now we can repeat this process and we'll say, okay, if I'm the man, let me consider the woman's possible options. If she chooses ballet, I, as the man, should I choose ballet and get a payoff of 1, or should I choose boxing and get a payoff of 0? Well, obviously 1 is better than 0, so I should choose ballet. So let's underline that one blue. And then the last possible scenario is, okay, what if the woman chooses boxing? I, as the man, should I choose ballet, or should I choose boxing? Well, boxing offers the higher payoff. 2 is greater than 0. So I, as the man, I will choose 2. Now here's what we'll notice. The Nash equilibria are the two boxes where both numbers are underlined. So there's actually 2 Nash equilibria in this particular game. And what's really interesting is that even though there are 2 Nash equilibria, both the man and the woman have a preference for which Nash equilibria they'd rather end up at. So the woman would rather end up in this scenario where they both choose ballet because she gets the higher payoff. And similarly, the man would rather end up at this Nash equilibria where they both choose boxing because he gets the higher payoff. But we'll notice that either Nash equilibria that they do end up with is better than the alternative of both of them choosing different activities where they both get a payoff of 0. Now, what makes this particular game in game theory so useful is that it actually has a lot of real-world applications. So as one example, consider the scenario where we have 2 firms who merge together and they form one new firm. So for example, instead of our players being a woman and a man, let's say we have firm 1 and firm 2. And let's say that when these 2 firms merge together, they can either choose to use the software that firm 1 was originally using, or they can use the software that firm 2 was using in their business. So instead of choosing between ballet and boxing, let's say they're choosing between software number 1 and software number 2. Now in this case, we essentially have the same scenario as the Battle of the Sexes, where both firms would be better off choosing to use the same software. So if they ended up at either of these 2 Nash equilibria, they'd be better off at either of these points than choosing to use different software. Because in that case, if they choose different software, it might be difficult for all of the new employees to be working with 2 different types of software in one business. But we'll also see that firm 1, they would prefer this Nash equilibria because they get to use their own software that they have been using. So they get a slightly higher payoff. But similarly, firm 2 would rather end up at this Nash equilibria where they're both using the software that firm 2 has been using because they get the higher payoff. But notice that no matter which Nash equilibria they end up at, they're both better than the alternative of just using different softwares. So once again, similar to the Battle of the Sexes, we can see that in this type of scenario, it would be better if the firms cooperated. Even though both firms have a preference on which software they end up using, when they cooperate, they're better off than when they don't cooperate. So that's the general idea behind the Battle of the Sexes game, along with one example of how it actually applies to a real-world situation.